Okay, good morning, everyone. Today we'll talk about an important topic, design of concrete slabs for punching shear, um, whether it's for gravity design or for seismic design. This is an important topic, and there have been, unfortunately, several collapses due to punching shear. Whether it's due to earthquakes or even due to gravity loads, as we will discuss. Okay, so some of the collapses are shown in the figures here. So those, all of them are related to earthquakes. Actually, the ones that are shown here. So during the 1985 Mexico earthquake, about 91 waffle slabs and solid slabs collapsed due to punching shear, and about 44 others, suffered severe damage. And some post-tension slabs also failed in punching shear during the 1994 Northridge earthquake. And even here we have an example of a parking structure that collapsed in 1997. And actually there was a similar collapse of another parking structure in 2015 due to punching. Sorry. Okay, the concept for the design of punching shear it starts from the concept that's shown here. So we have a load that's applied on the slab, and then the slab column joint cannot take that load, and then punching will happen through the slab, as can be seen. So the solutions to that varied over the time, and one of the solutions was like a mushroom slab, like it's shown at the bottom figure. Okay, so you have a thickened portion above the column capital, and then you have a column capital, and then you have the column below that. So this actually helps in increasing. This helps in increasing the shear capacity, um, of the slab, and will prevent punching shear. So this was one of the solutions that came to solve this problem. Later on, Kahn is the German engineer who came up with the steel reinforcement concept for punching shear, as shown here. Okay, so he developed the reinforcement type that's shown here. Okay, and that's how it's implemented in the slab. Okay, and then this was we have the slab reinforcement, and then the slab reinforcement the bottom reinforcement would be bent to become a top reinforcement like they used to do before. We didn't use this methodology anymore today for flexural reinforcement, and then use that reinforcement, the diagonal one here, for shear reinforcement for punching shear. And then later on, the development led to use of headed studs, okay, or double-headed studs, single or double-headed studs, as shear reinforcement for punching shear. So that was the other solution that was used later on. So what happens in punching shear here is, so we will have inclined cracks that are developed, okay, and then we have the negative reinforcement, which is the bent up bars. Here they will be separated from the slab, leaving no connection between the reinforcement and the concrete, which will lead to eventually to a punching shear failure. So that's the process of that mechanism. Now, lessons learned from past failures. My apologies about connection. Looks like there's an issue here. So some of the lessons learned were the prevention of using restriction of using waffle slabs without shear wall. So if you are using a waffle slab, you have to use a shear wall. Increase the depth of floor joist at the connections, and then we know now, upon the research and learning from these failures, that International Building Code (IBC) prohibits the use of flat plate as a lateral force resisting system in seismic design category D and F. Okay, it's not it's not as a gravity system, as a slab system. No, it's as a lateral force resisting system. So as a moment frame. So the slab and the column as a moment frame, that's prohibited. But to use a slab with with the flat plate without drop panels or without beams, that's fine. You have another system which is shear walls or moment frames to take care of the lateral loads in seismic design category D and F. That should be no problem. But as a moment frame, you cannot use it in seismic design category D and F, but you can use it in seismic design categories A, B, and C. That should be no problem with height limitations, of course. Okay? So, slab column connection in flat plates are subjected to high shear stresses produced by a transfer of the forces. So here you can see, so we do have shear stresses introduced into the joint. That's the top right. So these are direct shear stresses. And then we have shear due to unbalanced moment. So we do have the unbalanced moment due to bending or the drift, due to the drift of the building, as we will see later. So that produces flexural stresses as shown here. So if we add those together, we have such trapezoidal stress distribution on the slab. So as you can see, we do have an unbalanced moment on the slab that we have to consider in our design. So design codes that ACI 318 and the Eurocode 2, for those of you also who practice in Europe or working on a project in Europe, even if they are in the US or other parts of the world that use the Eurocode, this system of using shear reinforcement for punching shear is considered. And both of them, ACI 318 and Eurocode 2, permit the use of headed studs and and reinforcement conforming to certain standards, whether they are in the US or in Europe, following what's stated in 318 and EC2. Shear reinforcement is in the form of vertical rods, mechanically anchored at each end, um, can be used. So whether it's that this is an arrangement of the stirrups, shear reinforcement around the column to use um, for shear reinforcement, as you can see, and that's how this is done in the field. So you have the top bars, and then you have these the stirrups here, as you can see, that they go around the column to use okay, my apologies again. Um, that they go around the longitudinal bars, or actually the longitudinal bars will keep them together, and we have to maintain the contact between the stirrups and the rebars. Okay, so here, that's, if we look at that closely, that's what has been used before, start using the studs. So we have a movement at the end of the bend. So there will be some movement here at the end of the bend that's expected. The stress exceeds 0.4 Fy, the yield strength. The movement is reduced by attaching the horizontal bar. So if we attach a horizontal bar, which is the top bar, that will prevent the movement a little bit, but that's difficult to do. In practice, that's difficult to do. So if and which will result in slippage of the rebar, and of course that will affect the behavior of the slab during, especially during an earthquake, and then this will result. If we have to if we have to use stirrups, the longitudinal, the top reinforcement of the rebar has to be reduced. So we have to take that take that into considerations. Okay. So this problem can be avoided by providing mechanical anchorage. So if we provide mechanical anchorage, that can do it. Okay. So the other option is mechanically anchored shear reinforcement. That's headed studs here. Okay. So using headed studs like this will provide the right anchorage at the top, will not affect the negative reinforcement at the top of the slab, and it's the most effective type of reinforcement that can be used for a punching shear. This is the arrangement of this and the feet. Okay. Our apologies again. Um, yeah, this has actually has been happening since the morning. I had a couple of meetings before this. I had the same issue, so not sure what the issue is. We'll do our best going through this. So that's how the arrangement of the studs is depending on the need. We have to calculate, how many studs we need and how many rows of studs we need for per our design. So here you can see that the shear reinforcement is used to intercept the cracks. So the cracks will develop in the slab like this. So the reinforcement is used like that to intercept the cracks and prevent them from widening. And the cracks may happen anywhere along the depth of the slab. And the anchorage is essential at the bottom and at the top of the slab. And the anchorage is achieved by the heads, as you can see, the heads at the top and the bottom of the studs, and also by the bends of the hooks if we are using, stirrups. Now, what do we use for punching shear? So we do have provisions in ACI 318, but we also have ACI 421. That's a design guide um, by ACI. So this is the latest 421.1R. This was published in January 2020. Uh, there were like several versions, before this, but this is the latest, which guides you through how to design for punching shear or any things related to shear reinforcement in slab. Okay, according to this, the ultimate shear stress should be less or equal than the nominal shear. Okay, and when we say the nominal shear, this is related to the uh, the shear strength that's due to concrete and due to the reinforcement, if it's applicable. This has to be satisfied at a critical section that is d over 2 from the face of the column, and also satisfied at d over 2 from the perimeter of the last line of reinforcement. So if you look at the solid lines at the bottom figure, this is the last line of the reinforcement. Okay. So how do we calculate the punching shear stress, the applied punching shear? That's equal to the direct shear, okay, plus the moment, the contribution from the moment on each side in the x direction and the y direction, multiplied by gamma v, and you know gamma v is the contribution for shear, okay, which we know from slab design, and gamma v can be calculated using this equation. This is gamma f. So in slab design we use gamma f for contribution of the moments to flexural design. So we subtract that from one, we get the contribution for shear. So that's how we calculate this, and these are available in ACI and also in the appendix of ACI 421.1. So using the contribution of the two moments from each side and the direct shear, that's how we calculate VU. So all these parameters are defined here, and they are shown in the figure L1 and L2. That these are the length of the critical sections on both sides, X and Y, and D over 2 is the distance to the critical section. And so Jx, J1, gamma Vx, gamma Vy are provided for any shape of column, a corner, edge, etc., middle column, and an appendix of SCI 421.1R. Now, for an edge column, if the centroid of the critical section does not coincide with the centroid of the column, like as we see here, so O is the centroid of the column, and then away from that at the intersection of the figures here, okay, we do have the centroid of the critical section. If those do not coincide, then we need to calculate MUX and MUY like this, okay? So MUOX, MUOY, these are the moments at the centroid of the column, plus the shear force times YO and XO as shown in the figure. So we need to calculate those as such. And if we have a corner column, that's how we should calculate that. So the centroid of the cross section is somewhere here of the critical cross section, and then the centroid of the column is 0.0. So calculating MUX and MUY using this equation to be used in the calculation of V sub U equation. Okay. Now, what is the shear strength of the concrete here? So the shear strength of the concrete at the critical section at D over 2 from the face of the column should be the smallest of these values. Okay, I think you have seen this before in ACI. So this is related to the location of the column, of course, and also the perimeter of the column, and whether it's an interior column or an edge column. Okay, we do have all these parameters as shown here. Okay. In many cases, the 4 times lambda square root of prime C controls our design, but you have all the parameter here, so we have to check that and choose the smallest. Okay, so that's how the shear strength is determined. Now, outside the critical section or the shear reinforced zone, this is the strength of the concrete, 2 times lambda square root of prime C, which we also know it as the beam shear. Okay, so and the VU should be less than 5 VU and should be satisfied. If this is not satisfied, then shear reinforcement should be required. Okay, so first we check the concrete. If the concrete is enough, which is equal to the nominal design, the nominal capacity, 5 VN, which includes only VC for the concrete. If that's not enough, then we have to add reinforcement. So if we add stirrups, if we consider stirrups as shear reinforcement, ACI permits the use of stirrups as shear reinforcement when the depth D, the effective depth, is equal or greater than 6 inches, but not less than 16 times the diameter of the stirrups. Okay, these are the limitations for the thickness of the slab and using stirrups in the design. When the stirrups are used, ACI requires at d/2 from the column face, the ultimate shear stress should be less or equal than 6 times 5 times square root f prime c. Okay. Now the shear strength at critical section within the shear reinforced zone is equal to the concrete contribution to the strength and the steel contribution to the strength. The concrete contribution 2 times lambda times square root f prime c, and then Vs. That's, you know, this equation from beam design, but here we do have we have differences that P sub 0 is different, which is related to the perimeter of the critical section. Okay, so everything is defined here for the shear, reinforcement, the spacing, and S sub 0 is the distance between the first peripheral line of reinforcement and the column face. And so S sub 0 should be less or equal than half the effective depth, and S is the same thing. S sub 0 should not be smaller. The first line of reinforcement around the column, it should not be less than 0.35 D. Okay, so these are reinforcement and detailing for the studs. If we are using studs, here you see many provisions, you know, within this, like, you know, less than d/2, less than 2D, etc. So we have all these provisions shown schematically, and they're also presented in ACI 318. This is from ACI 318, 318 2019, the most recent one. So if you this is a figure R 8.7.7. So if you open the code, you will see all these figures. You can use these details even in your drawings, showing, you know, how to guide the contractor on using stud design, studs per your design. Okay. So ACI Chapter 8 requires stirrups and other bars or wires used as shear reinforcement shall extend to a distance d from the extreme compression fiber and shall be developed according to Chapter 25. So here this talks about, you know, how long should that extend. So should extend to a distance, effective depth of the member, and then should be anchored according to the anchorage and development length requirements of Chapter 25. Tests have shown that studs with anchored heads of area equal to 10 times the area of the stud itself, the shank itself, should satisfy the anchorage requirements. So here you can see at the top here. Okay. So here you can see the heads of the studs, how they are. Okay. So this is square root of times D. Okay. So this will provide, this number was taken from experiments. So if the area of the anchors at the top is 10 times the area of the stud itself, then we should be okay. Okay, the use of the shear devices provide higher capacity. So this is actually provide better capacity than stirrups. This has been F prime C instead of 2 times lambda times square root of prime C. So if we use shear reinforcement, we can increase the strength of the concrete. Okay. And also the maximum limit for shear 8 times square root of prime C instead of 6. So okay. Okay, ACI permits upper limits for S based on the value of V sub U at the critical section at d/2. So S should be less or equal than 0.75 D, three quarter times the depth if the stress applied stress divided by phi less or equal than 6 times square root of pi mc, and should be limited to half the effective depth if the stress divided by 5 is greater than 6 times square root of pi mc. So here you have to check your load and see whether you exceed that limit of 6 times square root of pi mc to see what so so we have that limit of increase to 0.75 d if the conditions here are satisfied. This is instead of using 0.5d, for everything. So you can increase it if the conditions are satisfied. Okay. Another thing that engineers have been using is shear capitals, right? I mean, probably you're familiar with that, or you have seen it. You will see it more and more in old buildings. So if you're investigating old buildings, you will see shear capitals. So now, so the shear capitals are used. So the shear capitals are used typically to increase the strength of the slab in shear um, without reinforcement. Okay, so to determine the capacity of the slab, so the capacity of the slab is in concrete is the smallest of these capacities that are shown here. Okay, which is the same ones that we checked before. Okay, these are the same that we checked before. There's nothing, there's, yeah, there's nothing different. Okay, so,
Yes, Doctor,
so
can you share the screen, please? Your screen dropped.
sorry.
Your screen dropped. Can you please share the screen?
Can you see my screen
Not yet.
now?
It's coming up. Yes.
Okay, good. So the so here this shows the type of capital that could be used and how the distribution of the cracks may happen. This is based on tests. So if we have a column supporting the slab, so the cracks could be happen diagonally from the edge of the column at an angle that's about 45 degrees. If you look at the figure below where we have a capital, so you can see the distribution of the cracks. How would that happen? And these things have shown that we have issues with those wedges here at the edges here. That's E, G, F, and also the other corner. That those actually will fail. During the tests. So with or without shear reinforcement, shear capitals are not recommended. Okay. So these days engineers don't use them much, but you will see them in many of the old buildings. So also we have that Migali and Gali in 2002 showed that shear capital failure is accompanied by separation of the wedges. So that's A, B, C, and D, E, F. Those will fail during tests. So they fail in a brittle failure. Therefore, these are not recommended for mid to high seismic areas. And analysis has shown that this type can be unsafe with the relatively low shear combined with high unbalanced moment. Okay, so that's why engineers stopped using those. So this could be unsafe with high shear and small unbalanced moment. Okay, so this shows actually how we can deal with this. So that's a shear capital, and then calculating the capacity at a distance that's equal alpha times d, the effective depth from the column face. So the maximum shear stress should be less or equal than the nominal design capacity. And then at d over 2 from the face of the column, that's the dashed line, it should be, the shear strength should be the smallest of any of these, which is the same that we used before. And then outside the capital should be the beam shear value, which is 2 times lambda square root f prime c, that we all know from beam design. Okay. Um, Now in ACI 421.1R 2020, also in previous versions, there are two methods for calculating the shear strength that were developed by a couple of researchers here. So they are related to alpha. Okay, as you can see, there's the alpha value here, and F prime C, the strength of the concrete. That's what they, and these are empirical relationships based on tests, and the equations are summarized here. So you can see that you have, if alpha is small, okay, so you do have high capacity here, okay, and then it keeps reducing up to the shear, the beam shear value, which is 2 times square root f prime c here, okay. And then the same thing for, for this one here. So we do have, like a smaller value, and then keeps increasing, with alpha here. And then that line, but it's less than 4. Here's the maximum is 4. Here, this is 4 here. They are less than 4. And then, but this is the 2, and they're still less than 2. So they are between 2 and 4, which is different representation to this. Okay. Now, requirements for seismic resistance slab connection. So the connections of the columns with flat plates should not be considered, as we said, as a lateral force resistant system in high seismic zone. Due to the lateral movement of the structure, slab column connection transfer vertical shear and reversal moments, okay, cyclic moment back and forth, as we'll see. And test has shown that with the column, that the column transfers constant vertical shear and cyclic moment reversals with increasing magnitude. So the building will move back and forth, and then so cracks will happen, okay, in the concrete. So as the cycles increase, okay, the magnitude of the moment increases. The magnitude of the moment increases, which will have a higher effect on the slabs, okay. Now, slab column connections provided with shear-headed studs behave in a ductile fashion, okay? So if we use headed studs, the drift during the seismic event can be accommodated. And the test has shown that the drift could be 3 to 7% without failure. And also the shear strength is the same. The shear strength calculation is the same, except that the concrete capacity is reduced due to the cracks that are developed during the cyclic event to 1.5 times square root f prime c, okay? So here you can see this is, same thing, it's the same philosophy even in the Eurocode, having the cracks, developed like this. And then we do have the concrete resistance indicated as VRDC, and then we have the stress resistance, and then we have the maximum capacity, that's VRD max also, that can be used, okay? And this is the arrangement of an acceptable anchor spacing for the studs according to the Eurocode, which is different slightly from ACI, but there are some proposals in modifying the arrangement in ACI to something like this, like a circular arrangement of the studs following what has been used in the Eurocode. Okay. So that's as you can see, this is more of a circular arrangement of the studs. Okay. Here the spacings are pretty much I mean they're very close to what has been used in ACI as well. Okay. Okay, so now design for seismic. During an earthquake, so we have significant horizontal displacement of flat plate column connections may occur, resulting in unbalanced moments, okay, which will produce an additional shear value. We have brittle punching shear can occur due to the transfer of the shear forces with the unbalanced moment, as we discussed. And for a flat plate column frame system is efficient in resisting gravity loads, okay, not seismic loads, and the significant moment transfer on the slab column joint when a slab is subjected to lateral loading due to wind or an earthquake. So we will have a behavior like that. So here you can see slab column connection. We can see, closer to the connection, the theta one, the rotation of the joint, and that reduces as we go away from the joint. So that's why for example, for wind or for low seismic, as you can see, that portion of the slab L2 with the column can act as a moment frame, but that's not allowed in high seismic areas. So as a result here to this reversal loading and that bending, cracks will develop in the concrete. When the cracks develop, the stiffness of the slab will be reduced, and that will increase the drift over time during the cyclic events, and we will have unbalanced moment introduced in addition to the direct shears. Okay. So this could be avoided by changing the dimensions of certain members, the material strength, punching shear design with or without reinforcement, and appropriate detailing of the longitudinal reinforcement, and then all the combination of the above. So we can change the dimensions, we can increase the material strength, and we can use also reinforcement. So we could use combination of all of them, not only changing one parameter to increase the strength. So ACI 421.2R, so the one that we talked about is 0.1R. 0.2R design guide addresses the punching shear requirements for seismic, okay? And that's related to the drifts. So here in this figure, we have unbalanced moment transfer. So we do have, for example, the gravity load moment diagram that's shown at the top. And then we have the earthquake or wind moments that are produced here, as you can see at the bottom, okay? So adding the wind or earthquake moments to the gravity moments, that will introduce an unbalanced moment, which will increase the stresses on the slab column joints. Okay, so that's so for a direction of loading that's in that direction. This is the behavior that we have, and that's actually that drift. So theta is related to the drift. So that drift is what causes the punching shear. That may happen. That's at the slab column connection, and that theta, that angle, as I mentioned before, reduces as we go away from the column. Okay, so the IBC requirements, we will talk about some of them. So the first thing is that slab column moment frames can be used in low seismic regions. Those are seismic design categories A, B, and C, but they cannot be used in seismic design categories D, E, and F. And slab shear reinforcement of Chapter 8 and drift requirements according to ICI Chapter 18 and 421.2R can be followed. Okay. So let's see, for example, if we have a frame like this, the design interstory drift is delta U, that's including the plastic deformation. ACI 318 permits elastic analysis. So that's what we typically do as engineers. We do elastic analysis, and then we amplify the displacement, the elastic displacement to, when we design for seismic. So the elastic displacement is equal to the ultimate displacement, which includes the plastic deformation divided by C. Okay, C is between 2.67 and 6.5. So IBC or AC7 standards. So we have delta sub U is less or equal than 0.0077 to 0.0025. Okay, that's according to IBC or AC7. C depends on the inherent elastic deformability of the lateral force resisting system. Okay, it depends on how detailed the system is for ductility. Okay, if it's highly ductile, then the drift limit is higher. If it's not, then the drift limit is less. So this is we do linear analysis, as we all know. We get the moment diagrams, we get the elastic analysis. So ME, the moment due to earthquake, is based on the cracked sections. Now the lateral force the system has been analyzed for lateral forces. Delta U and delta E are known. Now it's required to design it for seismic, okay, or to meet the seismic limit. So here, the provisions started from using this, this figure here, which is based on many tests, whether using what we call it. Shear reinforcement, whether it's headed studs or stirrups, or without. Okay, so you can see here different researchers did different tests. So you can see the slabs that were tested with shear reinforcement, they showed much higher, behavior, much better behavior above. Okay, much better behavior above. And then the ones that are without shear reinforcement showed much lower capacity. So this was the basis of the proposals that we have. So here, and one more thing, this is related to here. You can see the vertical axis is the ultimate drift ratio. So this is related. So you can see with the headed studs, curve 3 HSSR, we can reach high drift ratios in the slabs. At the same time, this is related to VU, the applied shear divided by the design concrete shear capacity, or the design concrete capacity. See, 5 VC, it's VC only, right? Only the concrete capacity. So as the load is higher, okay, the drift limit, it decreases. The drift limit decreases. This is very important. So if we have small shear on the slab, okay, we can achieve high drift ratios, okay, for seismic. If you are designing close to the limit, you have high shears, and so VU is very close to 5 VC, then the slab cannot accommodate much of the drift. Okay, so here another figure, which is the same thing: ultimate drift ratio in VU over 5 VC. Here you have slab with stud shear reinforced. So you can see slabs with studs, they have high capacity. Same thing, they reduce with the increase of the shear stress. And then slab without shear reinforcement, you can see how would that behave. And here we also have the IBC limits, the International Building Code drift limits. So we have the 0.025. So we have a range, but that's the maximum. That's the maximum. And this is the 0.015 limit. Okay. So you can see here for slabs without shear reinforcement, basically they barely meet the limit, but that depends on VU, how much shear is applied into the slab. Okay. So the procedure here, we have ACI 318 and 421.2R. We have two options for the design. Option A is a strength designed to resist VU combined with unbalanced moment to satisfy requirements of Section 8.4.4 of ACI 318. VU and MU factored forces transferred between the slab and the column. That's due to 1.2 dead load times E times 1 or 0.5 times the live load, depend on the occupancy. If it's an office building or public or public building where live load is more than 100 pounds per square foot, or plus 0.2 times the snow load if applicable. The design according to option A satisfies ACI 318 for all flat plate connections, whether designed or not designed as part of the lateral force resisting system. Option B, it's an empirical design based on parameters like the figures that we looked at and the drift, the ultimate drift. So VU, that's the shearing force due to factored gravity load. VC is the nominal shear strength provided by concrete. I is the strength reduction factor. Okay. Now, shear according to option B, which is an empirical procedure, the shear reinforcement is required when the ultimate drift is greater than 0.005 and delta U is greater than 0.035 minus 0.05 times the ratio between the applied shear and the concrete design capacity. Okay. So the code specifies empirical minimums also for the amount of the extension of the shear reinforcement. Okay. ACI permits the use of option B only for flat plate columns that are not part of the lateral force resisting system. Okay, just for gravity load. Okay, but we have to check the drift issues. It could be a slab. You may have moment frames taking care of the lateral loads, but punching shear during an earthquake may happen. So that's why we have to check the drift. This is very important. It's not like if the slab is not the slab column frame is the lateral force resisting system. And if we're providing shear walls or moment frames, punching shear will not happen. No, it may happen. It may happen. That's why we have to check that. So here it says if we are using this, the slab should not be part of the lateral force resisting system, but we have to check it. Okay. So ACI 318 gives also this figure for PT slabs and also non-pre-stressed concrete slabs, like mild slabs with mild reinforcement. So this shows you clearly, okay, the design story drift ratio, where shear reinforcement is not required and shear reinforcement is required. As you can see, it depends on the shear stress, the applied shear stress versus the concrete capacity in shear, and the drift ratio. It's very simple. So you calculate the shear stress, you calculate the concrete capacity, you know what your drift is, and then you will see if your slab requires shear reinforcement or not. Okay, the figure summarizes many of the things that we talked about, which were also based on tests. Option B specifies a minimum amount of shear reinforcement, V sub S, that's greater or equal than 3.5 square root of from C, P sub 0 times D. P sub 0 is the perimeter of the cross-section, D is the effective depth. And the extension of the shear reinforcement zone should be greater than 4 times the slab thickness. Okay, so the shear reinforcement you are providing with the stirrups or studs should be greater than this value, the 3.5 times the other terms, and the extension should be 4 times. How far we need to extend that is 4 times the slab thickness. So if you look at this, it's impossible to find a case that requires this extension by the design that's satisfying the shear reinforcement requirements of ACI. Okay, so, but it's an empirical approach. That's how it was. That's why we do have option A, which is more detailed and applies to many cases. Okay, so here, that's this shows the different options. So this shows option B. So if we follow option B, this is the figure that we looked at. This, some part that requires the enforcement, other does not. This is the 0.4 limit, okay? And this is option A. Option A is like that, okay? So here, the strength requirements chapter 8 are not satisfied in the red zone, okay? If we look at chapter 8 requirements, they are not satisfied according to this. Option B requires less calculations because it's empirical, but may result in connection that lacks strength. Now, this discussion is actually more in 421.2R, right? About the provisions that are in chapter 8 of 2018. In addition, it recommends a minimum amount of shear reinforcement when VU over 5BC is greater than 0.4, or when the ultimate drift is greater than 0.015. Okay. So these are the things here. So when we have this ratio is greater than 0.4 and delta U is greater than 0.035 minus 0.05 times the ratio of the shear stress over the design capacity, provide shear reinforcement that satisfies the requirements, which we talked about before. Okay, the extension, the amount that is required to be applied. Okay. Now, ACI 421.2 are specified minimum amount of shear reinforcement. What is the minimum amount that should be applied? So here we have different zones. Again, this is design story drift ratio in the vertical axis, and horizontal axis is VU over 5VC. So here what we have, zone 1 and 2 represent the case when VU is greater than 0.4 times 5 V sub C, with such high value of shear combined with reversal moments, the ductility can be ensured only with shear reinforcement. Okay, that's 1 and 2. So we do have here zone 1 and 2, the ratio is greater than 0.4. So ductility can be ensured only if we provide shear reinforcement. Zone 3, which is less than 0.4, okay, ACI 421 guide is consistent with 318 in recommending shear reinforcement in zone 3, okay? So the provisions are here, okay? They are similar in terms of providing the requirements for providing shear reinforcement, okay? So these are, some of the details that are presented actually in the ACI code, okay? So you can see that for an interior column, for an edge column, and for a corner column, okay? What is the extension of the reinforcement? You can see that greater than 3.5D in each direction. The vertical section, D over 2, okay? And the spacing between them, okay? So that's the moment here, applied moment here in X and Y, and that's the direct shear. And here this has to be less or equal than 2D for the spacing. Again, this is the extension. So what's required for the distribution of the shear reinforcement is shown in this figure here. Okay. We talked about the critical section, D over 2, the critical section from the outermost peripheral, we talked about that. The strength, VU, MU, how calculated according to this load combination. And also 421.2 recommends to verify that the amount of shear reinforcement and the extent of shear reinforced zone exceeds the minimum, okay? And here we do have the detailing requirements that I talked about at the beginning that you can use, and these are from ACI 318 2019, okay? And this flowchart discusses the design procedure, steps for punching shear design that we discussed, okay? So you can just follow this design procedure and, for example, you need to determine the drift, VU, MU, and then the capacity of the concrete, okay? And the drift ratio must be less or equal than 0.025. Then calculate the maximum shear stress, VU, at D over 2 from the face of the column. Then check if VU over 5 is less or equal than 10 times square root of prime C. This is the maximum capacity, okay? If If it's less, then continue. If it's no, then you have to reduce VU. You have to redesign, like increase the strength of the material, increase the thickness of the slab, or combination, and then continue until that is satisfied. Then is VU over phi greater than the nominal shear strength of the concrete without shear reinforcement? If yes, then design the shear reinforcement and ensure that the minimum is provided. That's it. If no, is VU over phi VC is less or equal than 0.2? If yes, and no shear reinforcement required if it's less than 0.2. So remember, the limit is 0.4. So if it's less than half of that, then there's no need for shear reinforcement. If no, then check the drift. Is the drift satisfies this equation that we talked about before? If yes, and no shear reinforcement required. If no, provide minimum shear reinforcement, and that's it. Okay, so that's the procedure for designing for punching shear. Okay, so with this, I conclude, and I'll be glad to um, have any questions you may have. Any questions? Okay, any questions? Okay, yeah, at the end, I would like to apologize about the technical issues that happened at the beginning. This is out of our control, but I'm glad things, were okay in the second half. If you have any question, feel free to reach out. You should have, the slides, for this presentation. Any question about the provisions in ACI 318, ACI 421? I am actually the chair of ACI 421. If you do have any questions, feel free to reach out for anything that's related to this topic. Okay, there are no questions. I will conclude here, and thank you very much again for your patience, and have a great weekend.